All right. So now that we've kind of talked about the quantum physics, quantum model, and that sort of thing, some of the stuff that's really, really um, crazy and weird. Now we're going to get into some stuff that's a little bit more practical and a little bit easier to wrap your head around. And this is dealing with stuff just on the atomic level. So some of this you've done already in math class or other classes, so I'm not going to go over it again, like half-life. Usually we do a whole lesson on that. You do calculations on that. I'm not going to worry about that because you do cover that in mathematics a little bit. And yeah, it is just something that we're going to skip. So for this lesson, what I'm going to focus on is just looking at decay, radioactive decay. So I'm going to go through the first part as quickly as I can so we can get to the radioactive decay part, and then we'll do that fairly quickly. It's a pretty easy concept. Yeah, and then that'll be it for this week. Okay, so basically these first few slides are introductory slides talking about how radioactivity was discovered, right? Becquerel in here is discovered uranium and other ones that had this energy that can penetrate different materials, right? Which we call radioactive, right? And you can see in here some other people that are important, like Marie Curie. So these people that dealt with radioactive and this ionizing and radioactive material early on. Most of them died from cancer from it, but they were able to learn a lot from it, and because of that, we have what we have today. Okay, so in the physics 30 curriculum, there's a big chunk in this introductory part that I cut out already, not even in these slides, where they want you to just to understand the fact that first of all, that radiation is natural and we're all exposed to radiation. So the idea of radiation being bad is it's not bad. It just high levels of it are bad. And so yeah, there's a little quiz or a little kind of survey that we get you to do usually, and you see how much radiation that you're exposed to, and it's pretty common, right? Even you look at your body, right? Your body has carbon and potassium in it, and it's giving off radiation as well too. And so because of that, we're able to do radioactive dating, right? Like this Alps Iceman, because we know how much radiation that your carbon is giving off, so 600 becquerels per kilogram of body mass, right? And because of the half-life curves, they're able to actually determine how long that the body has been, decomposing or whatever. So for this Iceman, they knew that he's 5,300 years old. Okay. Some other natural sources of radiation is from outer space, right? So there's cosmic rays, and we talked a little bit about that in the beginning of the third unit. Astronauts in the International Space Station, and hopefully you're able to watch that this weekend where they docked with the International Space Station. It was pretty cool to see that all unfold, but they have to be careful because they're exposed to more radiation than we are at the surface because they don't have this whole atmosphere that's protecting them. Same with pilots of flights, especially transatlantic flights where they're in the air for a long period of time and they're higher up in the atmosphere. They're exposed to more of these cosmic rays that are, there's radiation that can be damaging. Okay, this diagram here, or this map, is just showing you where uranium deposits and radium deposits are found in soils and rocks. And that's obviously a naturally occurring material as well too. Canada is fairly high. If you look at all the values in here, Canada is pretty high, and that's mostly in northern Saskatchewan where there's huge uranium mines that we find this radiation as well too. So Australia has quite a bit there. Kazakhstan has a large amount as well too. Some artificial sources of radiation, nuclear power. So in Canada, most of the nuclear power is situated in Ontario. And so obviously there's nuclear fission that's going on there, and fission and fusion are something that we'll talk about probably briefly next week. But so there's some radiation that's caused because of that. Submarines use nuclear energy, as do space probes as well. And that's what the next slide on here is, just showing you a space probe, a Cassini-Huygens space probe. So this space probe, it's showing you how many years it's going. It only has a 28.8 grams of plutonium, radioactive plutonium. Just to put that in perspective, your typical chocolate bar is like 60 grams. So it's like less than half of a chocolate bar, if you want to, visualize that, of radioactive plutonium, and that's able to power the satellite for years and years and years and years and years. Okay, it says it was what? Venus flyby in April 1998, and then beyond Saturn in 2004, and it's still going, right? All right. Not dwelling on too much of this stuff right now. This is just all background information about radiation. This is showing you as well too that when we do have nuclear energy, the spent rods, the spent nuclear energy that is very radioactive and it has to be stored somewhere. Because the half-life of it is hundreds of millions of years, right? So we stick it into mountains. In Canada, we stick it in the Canadian Shield, right? And we try and protect it from the groundwater and the like, but it's basically going to be around forever, right? Uh, this is an interesting piece of note. I don't or thing to note, but I don't know if you really know this piece of trivia. But when the internet kind of came online and became, I don't know, popular or whatever, it started to be usable by the everyday person, not just by the computer hackers and that sort of thing. One of the first things that was shared online was this book here, this information thing, how to build a nuclear bomb and other weapons of mass destruction. And so, there were people who were really nervous and worried about the internet, like, this is the end of the world sort of a thing. And then this came out that was, easily distributed and anyone could read. I could download it, read it if I wanted to. And people thought the internet was the worst thing in the world. It's interesting that was one of the first things that was really, viral, if you will, that on the internet. This slide here is talking about how we use radiation for medical purposes. And so we have different ways of measuring radiation. In the medical field, we use something called sieverts. Okay, so 10 sieverts is a lethal dose for most tissue. It would kill most tissue. Okay, so you can see in here, this is a rat, and they're doing trials and that sort of thing with cancer. And you can see on here the tumor and all that sort of stuff in there. And so using radiation therapy to try and treat it. We talked a little bit about this with ionizing radiation. So, the effects of this radiation breaking bonds in the DNA structure. And as a result of that, there can be, cancer can be caused. It's to do with the part of the DNA that deals with the reproduction of the cells. And they just continue to reproduce without stopping, right? There's no stopping mechanism. And that's what creates the large tumors and that sort of a thing. There's basically two things can happen when you're exposed to radiation, high levels of radiation. The cell can die, and that's the best thing that can happen, because if the cell dies, then that's the end of it, right? If too many cells die, then you can get really ill, or you can die as well. But if the cell dies, it can't replicate anything that has become mutated, right? Whereas if number two, the cell survives and damage is done to the DNA and it mutated, then that's going to, continue to reproduce and pass on, and then that's more dangerous. Okay. One of the curriculum objective points is that you're tested on in this section here is about comparing two radioactive sources and saying which one is more dangerous, right? And so we talk about that in the next little few lessons or whatever. We're not going to get to all of them, but essentially it's pretty straightforward, right? It depends on the kind of particles that are emitted. It depends on the amount, and it depends on the rate at which it's decomposing. Something that decomposes very quickly is more dangerous than something that decomposes over a long period of time, right? But I mean, if you have a lot of the material that decomposes over a long period of time, that can be worse than something that's decomposing very quickly. So there's a lot of, kind of things to think about in terms of your exposure to that. Okay. So that's kind of the introductory part of this. Now we're going to get into the actual radioactive decay part, which is, the main part of this lesson. So in order for us to do that, we just have to review the nucleus, nuclear reactions, that sort of a thing, which should be hopefully pretty straightforward for most of you. If you haven't taken chemistry since Science 10, then you might just have to brush this off a little bit, but it's not that difficult to do. Okay. All right. So we have these diagrams on the right here. Okay. And what we're doing is we're just reviewing the atom, pardon me. And so we're just doing some terms that you might have learned in Science 10. And obviously, if you took Chemistry 20 or 30, then this is, you know, this stuff really, really well. All right, so protons are shown in red, neutrons are in white. Well, if we count them, the protons in red, we see that they have the same number of protons in each of them, and protons are what determine what atom it is. So this is carbon, there's 6 here, and there's 6 here, so that's carbon. So they're both carbon, but this one has more neutrons than this one here. Okay, so that means that they're isotopes of each other. So isotopes are basically atoms that have different numbers of neutrons. Okay, and so their mass is different as well too. And because of that, they have different physical properties, and they act differently, right? A really good example of that is if we take hydrogen and we make hydrogen 2, okay, that's called deuterium. That is used in making something called heavy water. So if we make H2O out of deuterium, hydrogen, the water will have properties of being able to absorb more energy than regular water. Okay, so different properties for different isotopes. That's our thing. In nuclear physics, we call atoms nuclides. All right. So here we can see this broken down a little bit more. So these are from the previous slide. They're both carbon, but this one has 12 total nucleides or nucleons, pardon me. So protons and neutrons. This one has 14. Okay, and keep in mind that when we call an atom with a number here, this number here is telling us how many particles are in the nucleus, right? And the particles that are in the nucleus are protons and neutrons, right? So the bottom number here is your atomic number, which is the number of protons. So if we know that this top number is protons plus neutrons, and this bottom number is just protons, if we subtract these two, we'll get the number of neutrons, right? 12 take away 6 is 6. 14 take away 6 is 8 neutrons. This is a very simple calculation you learned in Science 10, but a very important one as well. Okay, so mass number is equal to protons plus neutrons. That's this number on top. And then the atomic number down here is just the number of protons. Okay. So this is hydrogen, one of them that I was talking about, deuterium here. So this is hydrogen 1, okay, hydrogen 2, deuterium. So hydrogen 2 just has a neutron where hydrogen 1 does not have any neutrons, it only has a proton. Okay, and then tritium has 2 neutrons and a proton, so it has 3 nucleons, pardon me, that's the number on the top, and then on the bottom here is the number of protons. All right. Now we're going to quickly learn that we're going to look at these two numbers, the top and the bottom number, just slightly differently, okay? And here's a couple more examples with lithium, lithium-6, and lithium-7. The difference is one neutron, pardon me. Okay, so now what we're going to do is we're going to talk about radioactive decay. So we had to do that first, learning about protons, neutrons, electrons in order to do radioactive decay, because we're going to be talking about those things. But the idea of radioactive decay is the fact is this idea that the nucleus of an atom is made up of protons and neutrons. Protons are all positively charged, neutrons have no charge. So what happens when you have positive particles really close to each other? We learned this in the second chapter or second unit, right? They repel each other. So why does a nucleus hold together when you have all these particles that want to repel each other? Well, there's a force that is acting that is holding it together, and that force is called the strong nuclear force. And the strong nuclear force is a force that acts between the protons and the neutrons, but it's a balancing act. And the larger that the nucleus gets, the harder it is for that strong nuclear force to hold it together. And so you get to a point, I think it's above 80 on the periodic table, and they start to have trouble holding together. And so they are unstable and they will decay naturally. Okay. And that's what we're going to talk about here. And then we're going to talk about the different types of the decay that are happening. All right, this graph here is showing you the difference between the electrostatic force and the strong nuclear force. And you might recall from a previous lesson that the strong nuclear force is the strongest force in nature. Okay, as you can see here, the strong nuclear force, in terms of its separation, it only acts over a very short or very small distance. Okay, but it's a very, very strong force. It's an attractive force. Okay. Whereas our electrostatic force acts over a longer range, okay, but it is a much smaller, much weaker force as a result of that. Remember that this is in the force between the nucleons here, right? So we're leveling off in this area right here, whereas we have a big dip in terms of the strong nuclear force, the attractive force. Okay. Now, one thing, again, we're not getting into this in great detail, but when we hear an attractive force, a strong nuclear force, we start to think, well, positive and negative, or positive, that sort of thing. But the force of attraction is the same between protons, between neutrons, and between neutrons and protons for the strong nuclear force. So there's no difference in between their charges in that regard. Okay. This is talking about how when these start to decay and disintegrate, we create something different, a different nuclide. We call it a daughter product. And we also produce energy that's being released. And that energy is in the form of what we call radiation. Okay, and so we're going to look at the different types of the radiation right away here. Unstable nuclides have too few neutrons in relation to the number of protons. So the ones that have more protons than neutrons, that's where we're in trouble. Okay, so that's what this is saying here. In general, the more protons in the nucleus, the more neutrons that are required to overcome the electrostatic repulsion. And I mentioned this already, it says 82 in here, but all elements with 82, atomic number of 82 or greater, they have too many protons for the number of neutrons, and they are all unstable. Okay. This graph is really important, and I dug this graph up a few years ago, and then the next year a graph almost identical to it showed up on the diploma. It was like I knew somehow. But this graph on here is showing you the relationship between the decay, different types of decay, and the number of protons and neutrons. Okay, so keep in mind here that in this chart here, the y-axis is the number of neutrons and the x-axis is the number of protons. Okay, so we get different types of decay. So we have beta decay, we have alpha decay in here based on what the different proportions of them. This black line right here represents if you had the same number of each. So you can see 82 protons and 82 electrons. Okay. But what you notice is that most of this decay happens above this line here. And when you're above the line, you have more neutrons than you have protons in here. Okay. So this is showing you, they're showing you that in order for you to have stability, right, you have 82 protons here, right? We'd have to go all the way up to this black line right here, which is stable, and you would need 126 neutrons, right? So you need more and more neutrons as the protons go up to keep it stable, right? If you have or you're above that line a little bit over here, right, then you're going to have a different type of radiation, right? So beta negative or beta positive decay, or alpha decay when you're in here as well too. Okay, and I think that's all that you really need to know in terms of this. This should make sense from what we're talking about. A stable isotope always has more neutrons than protons. That's why everything is existing above this line here. Okay. And also that when we have an unstable nuclide, right, it might undergo a whole bunch of decays before it ends up along this black jagged line, which is its stable line. So it doesn't happen just in one decay. It can happen over a series of decays. Okay, so that's important to note as well too. All right, so now we're just getting to the types of decay. This is the last thing that we're going to do in this lesson. So thanks for bearing with me. We have alpha decay, we have beta decay, and we have gamma decay. Those are the three types of decay that we're going to look at. Beta has a positive and a negative version of it, so we'll be looking at both of those as well too. Now, whenever we have decay, I mentioned this already, we're going to have what we're starting with, and the thing that we're starting with is called the parent nuclide. It's going to decay into a new nuclide, which is called the daughter nuclide, and it's going to give off energy at the same time in the form of a beta radiation, alpha radiation, or gamma radiation. All right, so we're going to look at each of those individually. Okay, so the first one we have in here is alpha decay. Okay, now an alpha particle is actually a helium-4. Okay, so when we write it, we're going to write it just like this, a helium-4. So 2 protons and 4 nucleons. So that's what our beta particle is. Now, you can write it this way as well too, as an alpha particle, and we could put a 4 and a 2 on it as well. It's the same thing as writing helium-4 and 2. Okay, now that's the radiation particle. The other particle is the daughter particle. Now, the daughter particle is just going to depend on what you're starting with. Okay, and so I'm going to explain this, how this all works now, and it's going to be the same for beta as well. So just pay close attention right here. The number on the top on here indicates the number of nucleons, that is protons and neutrons. Okay, the number on the bottom here is charge. Okay, so for charge, you have to think about the number of protons. Okay, so we used to call it the atomic number. That's what the number on the bottom is. And, you know, to some extent, there's nothing wrong with that. That is true. Radon has an atomic number of 86, but we're going to, excuse me, we're going to call that the charge. Okay, so we have conservation of nucleons on the top and conservation of charge on the bottom, and those are two of our final principles that we have on our sheet here for physics principles. So number 7 is conservation of charge, number 8 is conservation of nucleons, number 9 we talked about already, but that's the wave particle duality. All right, so really simple. You get a question and it says you're going to decay radon, okay, radon 222, and it's going to experience alpha decay. So what happens is you set up an equation and you say, okay, my parent is going to be radon 222, and you look up radon, it's 86. And then you, on the other side of the equation, you write out the alpha particle, which is helium-4 and 2. And then the daughter, that's typically what they're asking you to say, what is the daughter product? Well, you say the number on the top have to be equal on both sides. So if I have 222 here, I have to add up to 222 over here. So 4 plus what is 222, or 222 take away 4 is what? And we get 218. Okay, and the bottom part is the same. I have 86 over here and I have 2 over here, so this number must be 84, right? When you get the bottom number, then you can look up on the periodic table to determine what the symbol is, right? Because it's the bottom number, your atomic number, that determines that. Okay, so 86 on this side, 86 here, 222 on this side, 222 on this side, and that's it. Okay, the key is remembering or memorizing that an alpha particle is helium-4, right? Once you know that, then it's easy to do these questions. All right, and this slide is just going through what I just talked about, conservation of nucleons on the top and conservation of charge on the bottom. All right, so that is alpha decay. The next type of decay we have is beta decay. And I think actually, one thing that I didn't mention is that one of the things that we talk about is what level of penetration is there for each of these types of decay. And so for alpha, you're able to stop an alpha particle if you had a piece of aluminum foil. Okay, or even a piece of paper would stop an alpha particle. If we get down to beta negative, before I get into the equation and everything, if you look on here, it says a beta particle, it can penetrate several millimeters of lead. So each of these has a little bit more energy as we keep talking about them, and so it requires a little bit more to stop them. Okay, so a beta particle can be written as, I'm kind of going through this from the bottom up here, but that's okay. Beta particle can be written like this. So it's a Greek symbol for beta, which looks like that. Kind of looks like a bee with a tail on it. And a beta particle is essentially an electron. Okay, so it's not a nucleon, so it has 0 on the top. It's not in the nucleus, and it has a charge of -1. Okay, and that's why we can write it as an electron as well too. You don't have to write it as that Greek symbol for beta. Okay. The way that the beta particle is created is what happens is when a neutron decays into a proton, an electron, and an antineutrino. Okay. Now I'm introducing something new here called an antineutrino. That's what this is right here. So the symbol for neutrino kind of looks like a V. It's a little bit, kind of italicized of a V. Okay, and an antineutrino, any antimatter, the way that we show it, we put a line over top of it. So we have an antineutrino like that. A regular neutrino would just be that kind of italicized V, that's it. Okay, now I'm not going to get into neutrinos and antineutrinos too much because that's another whole, half a lesson or whatever, or more than that if we really got into it. But what you need to know is that neutrinos weigh hardly anything at all, even less than an electron, and they move super fast. They are so small, in fact, that they can pass through the entire Earth. They can have one that goes from here, goes through the center of the Earth and out the other end without interacting with anything. So really peculiar particles that we're just starting to learn more and more about. So it's a kind of a new area of study in physics as well too. Okay, but this neutron decays into a proton, and I want to show you this because this is important as well. Where do I have some space? Maybe I'll do it right here. So if we have a neutron here, neutron will have a 1 on top because it is a nucleon, but on the bottom it has 0 because it has no charge. So if it decays, these are the numbers that have to balance on both sides, the 1 on the top and the 0 on the bottom. Okay, now we said that we're going to create this beta particle, right? Which is essentially an electron. So let's write that. This electron here, it has a 0 on the top and it has a -1 on the bottom. Okay, so it's creating this beta particle, right? But it's also creating another particle because these things don't balance, right? So we have to, obviously on the top, we have 1 on the left-hand side, we have to have 1 on the right. And on the bottom here, we have 0 here, but we have a -1. So we're going to have a +1 here in order to add up to 0. Well, what is a nucleon that has a charge of +1? That's a proton. Okay, so when a neutron decays, it decays into an electron and a proton, and then also a neutrino, which has 0 and 0. Okay, no charge, and it's not in the nucleus. All right, so what this is going to lead to, and we might get to it, we might not get to it this year in terms of Physics 30, is that we have these subatomic particles that are decaying into other subatomic particles, and they're made up of other smaller things as well too. And this is part of the whole decay series. Okay, now we don't write those things in here, but we can see that when we're when we're balancing out these values in here, right? If we have one extra proton, right? If we're creating a proton from a neutron, what's going to change? The number on the top is not going to change because a neutron and a proton are both nucleons in the nucleus, but a neutron has a 0 charge and a proton has a +1 charge. So the charge is going to go up by 1. And you can see that here. The parent has 90, but the daughter has 91. It went up by 1. Why? Because it has 1 more proton than the parent. And this can be confusing for some people because some people get in their heads that decay must always be going down, 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 down. But in fact, with beta decay, the charge is going up. Okay, we have this -1 over here along with the 91. We'll keep it still at 90 on both sides, but the daughter actually has a charge of 1 greater than thorium. Okay, this is beta negative. Okay, and on the next slide over here, it's just going through the same thing, conservation of charge like I talked about. Okay. There is also beta positive decay, if you recognize that from that chart that we did. Okay, beta positive decay, it's exactly the same as beta negative, but instead of it creating a electron, it's going to produce an anti-electron, which we call a positron. And remember that any antimatter particle has an equal and opposite particle, and opposite only in one characteristic, and that in this case is its charge. So instead of having a -1 charge for electron, we have a positron with a +1 charge here. Okay, and so we balance this all out. The other thing that's different is that it doesn't emit an antineutrino like beta negative does. It emits a neutrino. Okay, so that's opposite as well too when we do this. What happened here is that for us to go from a for beta positive is we had a proton, which has a 1 and a 1 charge here. It's decaying into a neutron, right? So if we draw our positron, which is 0 and +1, in order for these to balance, right, we'd have to have a 1 on the top there and a 0 on the bottom. Whoops, I didn't mean to make it as a fraction. 1 and a 0, which we know is a neutron. So it's the opposite of beta negative, where we had a neutron becoming a proton and electron. Here in beta positive, we have a proton decaying into a positron and a neutron. Okay, and also a neutrino. Now, I'm not going into this at all, but there are a whole bunch of other types of decays as well too. But if you're ever given a random decay, and they ask you to say what is the daughter product or whatever, you're just balancing the numbers on the top, right? The left-hand side and the right-hand side. So we have 41 here, 41 here. 20 and -1 is 19, and we have 19 there. Okay, so we don't go into it in Physics 30, but there are a whole bunch of other types of decays. And the last decay that we're going to talk about today is gamma decay. Gamma has the greatest amount of energy. It requires many centimeters of lead. Okay, so it requires a lot more. A gamma particle looks like this right here. It's kind of like a little loop on the bottom. It's a Greek symbol. You'll notice on here though that we have cobalt 20 or cobalt 60 here, and we have cobalt 60 over here. Gamma uh, gamma radiation is just energy. It doesn't have charge. It's not a nucleon, none of that stuff. So it doesn't change the parent and the daughter other than the amount of energy that it has. Because this energy is now separated from the parent here, the daughter is going to have less of that energy. The energy on both sides has to balance out, right? To have conservation of energy. So the daughter product is going to be less energy, which we say is unexcited. It's kind of uh, an interesting term for that. All right. The only other thing, I guess, with gamma radiation is that gamma radiation typically occurs at the same time. I apologize. It occurs at the same time as an alpha or a beta particle, right? So if we go to this next slide here, it's giving you some commonly encountered radionuclides. And you can see here, wherever we have gamma radiation, we usually have either an alpha or a beta, right? In fact, there's no examples on here where we just have gamma. It's always occurring alongside another one. So if you had a question that's asking for the equation and it says there's gamma and beta decay, you'd write your beta decay equation where you balance everything, and then you just tag on the gamma decay right at the end. You just tag this on at the end because it's 0 and 0, so it's not going to affect anything either in terms of balancing. All right, this is an example of something called a decay series. Now I've got the yawns, I apologize. Okay, but basically what this is showing is that we start with uranium-238 and it's showing all the decays that are required in order for it to become stable, which is way down here as lead-206. So each one of these is a decay. Now what's interesting to note with this is that we have the mass number on the Y and the atomic number on the X. Sometimes they're switched, so these graphs can look kind of opposite, so you have to be careful when you look at them. But we know that for alpha decay, the mass number is going down each time. And for beta decay, the mass number is staying the same because you're just going from a proton to a neutron or a neutron to proton. So that number staying the same, right? So these ones that are going across here are all beta decays, and these ones that are going down are all alpha decays in here. Okay. All right, so just a couple of examples, and then that'll be it for today. Complete the balanced equation it should be. So we have bismuth here, and it is undergoing alpha decay. So we want to find out what the daughter is in here, right? So we have 210 minus 4 would be 206 on the top. Now that's not going to tell you what it is on the periodic table because that's the mass number and it could be any number of isotopes. So we have to do the bottom number here. 83 take away 2 is 81. Okay, now we can go to our periodic table and find 81, which is thallium, right? So this is thallium in here. All right, so to complete the balanced equation, we're just doing a conservation of nucleons on the top and a conservation of charge on the bottom. Okay, and it says what type of radiation is this? Well, if it's helium in there, that's alpha decay. All right, let's take a look at this one here. Oh, they already filled in the answer for us here, right? But if we had uranium-237 and then we're undergoing beta negative decay, say, well, we have to balance on the top. So 237 take away 0 is 237. And then 92 take away a -1 would be 93. Go to your periodic table. What is 93? Oh, that's neptunium. Okay, so neptunium-237 would be the daughter product. All right. So those are really easy to do, those decay equations. You just have to balance the numbers on the top and the bottom. Like I said, the only thing you have to memorize is your alpha particle is a helium-4. Okay, Your beta, you have beta positive, so that's a 0 and a positive 1. You have beta negative, which is 0 and negative 1. And then we have gamma, which is 0 and 0. So these are the things that you would have to memorize in order to do those equations. Not very difficult to memorize. All right. So, excuse me, this video is getting really long, isn't it? This slide here is just talking about the penetration of these different types of radiation, and we talked about this a little bit as well too, right? But what we were talking about is what is required to stop it, right? So alpha particles, you would just need a piece of paper, aluminum foil. Beta, you could do it with a block of wood or maybe some millimeters of lead. And gamma, you needed centimeters of lead to stop it. Now, this is talking about how much it penetrates into the skin and that sort of thing. So alpha particles travel about 5 centimeters in air. They cannot penetrate the skin. Beta travel about 30 to 50 centimeters in air. There's still little penetration of the skin. So, electrons don't really penetrate the skin. And then gamma particles could travel great distances. Excuse me. And they can penetrate the entire body, right? There's another thing in here for ionization. So alpha particles have a high chance of ionizing electrons, whereas gamma particles have a low amount. And this might seem counterintuitive because you say, well, gamma has so much energy, so wouldn't it have a higher chance of ionizing electrons as opposed to alpha particles? And the reasoning for that is just sheer number of them, the sheer number of alpha particles compared to the sheer number of gamma particles as well. So the gamma particles, the chance of one hitting an electron, striking an electron, and it being the exact amount of energy is very, very low. This goes back to when we talked about the energy levels last week, right? Gamma radiation is a type of electromagnetic radiation. And so if it strikes an electron, it has to have the exact amount of energy in order to ionize it, right? Whereas an alpha particle or a beta particle is actually a particle and its momentum. And so if it strikes an electron, it just has to have the minimum amount of energy to ionize it, and then it is ionized. Okay. Gamma radiation has to be absorbed by the particle in order to ionize it. All right. And I think that's talking about that a little bit down here as well too. Charged particles are better ionizers. For this reason, alpha particles use almost all their energy to ionize atoms. Beta particles use some of their energy to ionize. Gamma radiation is not charged and therefore ionizes infrequently. Okay. The amount of energy remaining after ionization is directly related to the amount of penetration of the radiation. So more energy that is remaining after it, then the greater that it is able to penetrate, which makes sense. Gamma radiation has such a high amount of energy, there's still a lot left if it does ionize it that it penetrates with. Oh, and this is that last little thing. This is dealing with, alpha particle going to be stopped by paper, et cetera, et cetera. Okay. So I think that's it for this lesson, and that's it for this week. I'm not going to be giving you any big assignments this week, other than just some questions from your work booklet. This is your grad week, and so I don't want to be loading you up with a whole bunch of work. I know this was still a lot of videos and stuff to watch, so I apologize for having to go through all of that, but it was my goal for all this, even though it's only 30% that we're allowed to do, for us to at least try to get through the material. I'm just not going to be assigning you 30% or more than 30% of the work that you would typically do. As you may have noticed, I've completely dropped off doing the multiple choice review sets. Just some things that if I'm not preparing you for the diploma exam, I don't think are necessary. And, me trying to get the work level down to a 30%. Okay. If you have any questions with any of the stuff in here, a lot of it is theoretical, so it just takes some wrapping your mind around and that sort of thing. But any questions you have, please send them my way, and I'd be happy to try and to help you figure that out a bit. Okay, I hope you have a great week, and I will see you on Thursday at the grad parade. See you there.